Okay, so this here is a map of ocean fertility. These like reds and oranges and yellows, that's where phytoplankton, shokubutsu plankton is thriving. And down here in warmer oceans, you see this blue, these are ocean deserts. Nothing's growing there, so remember that. Remember also this, Japan has to cut its carbon emissions by 73% by 2040 and down to 0 by 2050 by law. Now, abating Japan's emissions from sectors like chemicals, steel, the hard to abate sectors, is going to cost between 110 and 160 billion US dollars. That's as much as Japan spends on public education. It's twice the defense budget. This is impossible, okay? So Japan needs something much better. You have the exact same effect on the atmosphere if you take a ton of carbon dioxide out of the atmosphere durably as if you never produced it in the first place. And let me tell you how to do that. It's called end-fixed phytoplankton carbon. Now, phytoplankton are microscopic, but when they bloom, you can see them from space. They're photosynthesizers, so they naturally capture carbon dioxide, and when they die, they sink. But they could be doing so much more, because up to half of the surface of the planet is made up of these marine deserts, where very little phytoplankton grows, because the waters don't have the nutrients it takes to sustain them, okay? So if the main nutrient that's missing is fixed nitrogen. If the waters were able to fix more nitrogen, then they would be able to capture more carbon. And you can do that, in fact, in the waters by adding the nutrients that these phytoplankton need. These are simple things like iron and phosphates that don't cost a lot of money. That's why the method is so low cost. Now, Japan's Ogasawara Islands and Minami Torishima are biogeochemically perfect places to do this. And at Anthropocene Institute, where I work, we actually were supporting a group called Growing Oceans that's finding ways to do precisely this. But the reality is that the difficult part isn't doing it. What's difficult is measuring it. Phytoplankton captures carbon dioxide for the long term when it dies, and it sinks down through the water column as what is known as marine snow. This is a process that happens hundreds of meters below the surface in complete darkness. So measuring that is a major scientific challenge. This is how we do it now. You take a funnel and you drop it several hundred meters down below the waterline, you wait, then you haul it back into a ship, you spend the next 6 months in a lab analyzing the results, and then you get an answer. This works for scientific research, but this is not going to scale for a gigaton scale carbon dioxide removal project. So you can measure how much phytoplankton grows with satellites, but they don't see below the first optical depth. So here's what we're going to do in my program. We're going to develop a new set of sensors that can capture these carbon fixation processes at basin scale. So these could come in several forms. They could be physics-based models that scan the entire patch of ocean at once, or they could be hyperspectral optical sensors that can analyze water chemistry throughout the water column, or you could do it with swarms of low-cost sensors. Whichever way you do it, you're going to generate a huge amount of data. So we also need to generate a next generation AI ocean model. It'll be GPU accelerated. That's going to allow us to actually integrate all that new data and produce an estimate of carbon fluxes that has measured uncertainty. And this bit is key because realistically, what you can get out of a system like this is an estimate. It's going to be a probability distribution. And there's going to be a 95% confidence interval. So the reality is that you're only going to be able to credit the lower end of the 95% confidence interval. So the more you can squeeze this distribution together, the higher the value of the creditable carbon that you can certify that you've captured. Okay? Now, the biggest risk is uncertainty. It may not be possible to reduce the uncertainty enough to make this work as a source of carbon credits. It may be that carbon takes longer to sink down through the water column than we're expecting. And the ecological challenges are, well, the knock-on effects are not well understood. They could be negative, they could also be positive, because phytoplankton is a base of the marine food chain. Ultimately, everything in the ocean needs phytoplankton, including you. It turns up in your plate as sashimi. It will take 30 months to deliver this program. After Q4, we're going to have a go, no-go gate for sensors. After Q6, we'll have a go, no-go gate for the models. In this third year, what we want to do is want to bring Japan's big industrial companies, because they have a legal obligation to offset, okay? So they're the ones who are going to be most interested in making something like this work. It's a bottom line problem for Japanese industrial firms. Now, how big is the global market? Usually you hear this aspirational figure of $100 a ton. At $100 a ton, 10 billion tons a year is a $1 trillion problem. This is what's called the $1 trillion question of carbon removal. Now, I want to suggest to you that this is a fantasy. There's no willingness to pay $1 trillion for this. What we need is a $10 ton, which makes this a $100 billion question, just a much easier question to answer. Now, this is about much more than Japan's nationally determined contribution and the GXETS. This is about protecting the Earth from the effects of climate change. Now, this program allows Japan to lead a push to decarbonize, not industry, but the atmosphere. Thank you.